This brings us to the first law of thermodynamics, which we often phrase as there is no free lunch. So thermodynamics, dynamic is referring to change, right? And thermal referring to energy. This is the study of energy and its interconversions. So the first law of this type of study is the law of conservation of energy. The total amount of energy in the universe is constant. You can't design a system that will create more energy than it uses. It's not possible. With energy, you cannot get something for nothing. There is no free lunch. You know, my kids went to public school and elementary school, and everybody in the school got free hot lunch, right? Was it free? Well, it didn't cost the students anything, but the taxpayers are paying for it, right? Somebody's got to pay for it. Same idea here with energy. You can't get something for nothing. State functions. Well, let's talk about mountain climbing. We're just jumping all over the place here. We got billiard balls, light bulbs, and all kinds of stuff. So mountain climbing. So here's a mountain, 10,000 feet tall, and there's two ways you can get up there. You can take the path, which is a fairly strenuous hike, a lot of switchbacks and snakes back and forth. Path A, you're going to walk 12 miles. But starting at the bottom and getting to the top, the change in elevation that you experience will be 10,000 feet. Or you can take path B, which is more mountain climbing, right, and just go straight up the side. That distance is only 5 miles, but it's a harder 5 miles, right? Your change in elevation is still 10,000 feet. It doesn't matter how you got there. My preferred method would be to call a helicopter. I'm going to be over here. The helicopter is going to pick me up and fly me up and over here and set me gently down on top of the mountain. And I have also experienced 10,000 feet of elevation change, right? But those 3 different paths were very different. A state function does not depend on how you got from the initial to the final condition. It only depends on what the initial and final condition are. It doesn't depend on the process, the path taken. The distance traveled is not a state function because path B, 5 miles, path A, 12 miles. It does depend on how you got there. So internal energy, which we're going to symbolize with a capital E, is going to be the sum of all the kinetic and potential energies of all the particles in the system. And what just happened? This internal energy is a state function. It only depends on the state of the system and not how the system got from one state to another. So we can talk about the change in internal energy. We're using this Greek, this is a capital delta, and that almost universally means change in. So when we say delta E, we mean the final amount of internal energy minus the initial amount. And that can be positive or negative. The energy can go up or the energy can go down. So in a chemical system, we're looking at reactants being the initial state and products being the final state. So this is the combustion of carbon, so carbon plus oxygen to form CO2. Carbon and oxygen have higher internal energy because of their chemical potential energy than the product does. So initially the system has energy up here. After the reaction occurs, the system has energy that's down here. The system has lost energy. Where did that energy go? It went into the surroundings, which is everything else in the whole universe, right? So it just like catches everything, right? So we see that energy is flowing from the system to the surroundings. The change in energy for the system is negative, because just like money leaving your account is a negative, energy leaving a system is negative. But for the surroundings, their energy change was positive, because the person who got the money that was removed from your account, they've got a plus on their end, right? So whether it's positive or negative depends on what side you're on. This is known as an energy diagram. And you can think of it as being a bit like an altitude diagram, where, this is so many feet above sea level, and that's so many feet above sea level, and this would look like coming down the mountain, right? Doesn't matter how this happened in here, just that it started here and ended there. The reactants in this example have more energy than the product, so energy's lost. Delta E for the system is negative. Delta E for the surroundings is positive. The value there, the absolute value, the magnitude of that number is exactly the same. But one is positive and one is negative. It's like transferring money between accounts. So if I said, well, let's see here. We could say the change in money for Jody is equal to negative the change in money for Brigitte, just because she's sitting in front of me.
No, we like money.
Yeah. So if I give her $10, what is the change for me? Yeah, it's gone. I've lost $10. Then what is the change for her?
Positive.
Plus. Whoops. Got the dollar sign. Isn't it weird that unit comes first? So the amount of money being transferred is equal, but it's negative for me and it's positive for her. So we say that the change for one is equal to -1 times the change for the other. This negative sign does not mean that this delta money B is a negative number. It doesn't mean that this is a positive number. Both of them, one's going to be positive, one's going to be negative, but it could be either way. Okay? Any questions?
So why is that negative sign there again?
That's a great question. Why is that negative sign there? Because the energy that is lost by the system is equal to the amount of energy that's gained by the surroundings. But there's a direction. So it was negative for me, but positive for her. We can't say that -10 equals +10.
Oh, I see.
So this negative is saying one is positive, one is negative, but they're the same number. Okay, and that one is just, I've tried all kinds of ways of explaining that, and I haven't found a good one yet. Oops. So let's think about doing the reaction in the other direction, where we're starting with carbon dioxide and we're forming carbon and oxygen. Well, carbon dioxide still has lower internal energy than carbon and oxygen, just because of how its protons and neutrons and electrons are all arranged. So now our reactants are lower in energy and our products are higher in energy. So we went from low to high as the system. So the system is gaining energy. Delta E for the system is going to be a positive number. Where did the energy come from? It came from the surroundings. So the change for the surroundings is negative, but the amount is the same. If reactants are higher in energy than the products, the system's losing energy, and so delta E is negative. Yeah.
I'm sorry, so could you go over how you would notate that? So you're saying that one has to be negative, one has to be positive.
Mm-hmm.
Would it just be, you just put the equal sign between them, or definitely?
So let's say that 5 joules of energy is being transferred. Oh my, what did I do? So energy, again, is like money. The system's like your bank account. Money leaving your account shows up as negative. Money coming into your account shows up as positive. So let's look at these fictitious internal energy gauges that are describing the initial conditions for a chemical system and its surrounding. So here, the chemical system starts out 3/4 full, and the surrounding starts out 1/4 full. Which energy gauges correspond to the final conditions following an energy exchange in which delta E for the system is negative? So if delta E for the system is negative, that's this top one, is this meter going to go up or down? It's going to go down because it's losing energy, right? So we can look at our 3 choices here and see that for A and B, our system energy gauge is going down, so that's good. But in this one, it's going up. So that tells me that that one's wrong. Now we've got 2 of them here. If the system is losing half a tank of energy here, no, I'm sorry, it's going from here to here, a 1/4 tank. If this is losing a 1/4 tank of energy, what happens to that energy? It goes to the surroundings. So if this loses, it'll go down here, and it's going to look like A, right? B is not possible because the system lost energy and the surroundings didn't gain the energy. And you can't say, well, it went into a different set of surroundings. No, the surroundings are the rest of the universe. It covers everything. Question? No? Okay. So the correct answer is going to be A. If one goes down, the other goes up. So heat and work are ways that the system and surroundings can exchange energy. So we give the symbol Q to heat and the symbol W to work. W for work really works for me. Q for heat, I don't know why they did that, but I do know that H is used in a lot of other places. So maybe that's why. I always want to know why, but never enough to actually go look it up. Okay, so Q and W are not state functions. The heat and the work do depend on the process. So that's like the distance traveled by those hikers. It depends on how you go, not just on the beginning and the end. But the total change in internal energy is equal to the sum of the heat and the work. So these are the sign conventions. So for heat, if the Q is positive, that means that the system is gaining thermal energy. So thermal energy is just a form of money, right? And if the system is, you're the system, if you're gaining the energy, you're gaining money, that's positive. If the system is losing thermal energy, then Q for the system is negative. That one's pretty straightforward. It matches up very nicely with delta E. The only difference here is that we're talking about, this is specifically thermal energy being gained, where this is just energy in general. So work, how do we keep those signs straight? W is positive if work is done on the system, and negative if work is done by the system. So instead of thinking of work done on the system, you could think of work done for the system, right? So if you come and mow my lawn, you're doing work for me. How do I experience that? That would be positive, right? I am gaining something, a nice mowed lawn. But from your perspective, that's negative because you had to expend a lot of effort to do that, right? Yeah?
So can you give an example in terms of chemistry, like how that would look like?
For the work, we actually don't use work much in chemistry because work is really a force applied over a distance. So like here's a bottle of acetone and I can push the bottle of acetone. So if I am the system, I'm doing work on the bottle and the rest of the universe. And so W would be negative for me and positive for the surroundings. I'm not sure with this example how that could do positive work for me, but the one way at least works. You know, mowing a lawn or maybe giving a back massage, you know, rubbing shoulders, right? So if I'm rubbing your shoulders, I'm doing work on you, and that's positive for you, but it's tiring for me, right? If we switch and do it the other way around, now it's positive for me, I'm getting the massage, and negative for you. So let's look at this in action. This is not a chemistry example, but there's just not really any good chemistry examples. The problem with chemistry is that so much of it is abstract because it's things that we cannot see. That's one of the nice things about Newtonian physics is, you know, balls rolling across tables, and you can actually see them, right? In chemistry, we're talking about an atom of helium vibrating, right? Nobody can see that. So we're going to use an example that we can visualize. So back to the pool table. So we've got this white cue ball, and it starts out with an initial kinetic energy of 5 joules. This is the energy of motion that it has. As it rolls across the table, it's going to slow down a little bit, right? Because no matter how smooth that table is, eventually the ball's going to stop, right? Because there's friction between the ball and the table. So that friction will cause energy to be lost as heat. So the ball rolling over here is losing 0.5 joules of energy to heat. So when it impacts the other ball, it has 4.5 joules remaining. And it gives those 4.5 joules to the purple ball, so now it has 0. So the work, the white ball did 4.5 joules of work on the system, on the purple ball, and it lost, which is part of the surroundings, and it lost 0.5 joules to the table, which is also part of the surroundings. The total energy change was negative 5 joules because it ended up at 0, and 0 minus 5, negative 5. Does that make sense? Let's look at a different table. This is a rough table. This one's like really old or it's been abused or something, and the felt is just really messed up. So now when you roll that ball, it's going to slow down more. So, you know, think about taking, say, a tennis ball and rolling it on the linoleum in the kitchen, right? It's, you know, you give it a little push, it's probably going to roll all the way to the wall. Then move over to the living room where there's carpet and give it the same push. Is it going to roll as far? No, because the carpet has more friction, right? So this is like the carpeted room. You're rolling the ball. It's going to lose more energy as heat as it rolls. So here it started with 5 joules. It's losing 3 joules as it rolls along. And so when it gets to the collision, it only has 2 joules left. Mm-hmm.
Will it always be in terms of heat?
Yeah. Yeah, so the loss of energy due to this friction will be heat. Yeah. So when it impacts, it has 2 joules left, and it does 2 joules of work on the purple ball. So if we look at what's going on now, the work is negative 2 joules, because that's the work it did on the other ball, and Q is negative 3 joules. So Q and W are different than on the previous table, but delta E is the same. Started with 5 joules, ends with 0. Delta E is final minus initial, 0 minus 5. And so here we've got that delta E sys is equal to negative delta E surroundings, right? Delta E for the system is negative 5 joules. Oops, let me do this first. Negative 5.0 joules. Delta E for the surroundings is positive 5 joules. Okay? So delta E was the same in both conditions, but Q and W are not. Delta E is a state function, only depends on what you've got when you start and what you've got when you end up. Doesn't matter how the energy got transferred away or came in. So here's a little problem. A cylinder and piston assembly, we're defining that as the system, is warmed by an external flame. The contents of the cylinder expand, doing work on the surroundings by pushing the piston outward against the external pressure. If the system absorbs 559 joules of heat and does 488 joules of work during the expansion, what is the value of delta E? Now, we really don't need to understand most of what that's talking about. I mean, it'd be great if we do, but don't let that trip you up. We verbalized the whole problem, whether we understood it or not, and then we're going to look at the numbers. So those are the numbers, and then the other thing I want to look at is what's the question? And the question is, what is the value of delta E? Well, it says that the system is absorbing 559 joules of heat. What is the symbol for heat? Q. So Q is 559 joules, but then we have to ask ourselves, is that positive or negative?
It absorbs it, so it's positive.
Yeah, it absorbed it, so it's positive, just like, $559 coming into my bank account would be a positive thing. If anybody wants to make that happen, just let me know. And then it says 488 joules of work. Well, what's the symbol for work? W. So W equals 488 joules. And again, we have to ask ourselves, is this positive or negative for the system? It's negative, because the system is doing the work on the surroundings. Doing work on the surroundings. The rest of those words, don't really matter. So that's negative. I put a positive sign here, not because I need to, but just so when I look at it, it's like, oh yeah, it's not just that I forgot to look, I decided that one was positive. Right? So we want delta E. What is delta E in terms of Q and W?
Q plus W.
It's Q plus W. So that's going to be Q, 559 joules, plus negative 488 joules. And if I remember correctly, that's 71 joules. Any questions?